Hello, 1, 2, 3, 4. Hello, hello.
स्पीकरला घ्या ना, त्यांनी इथं केबल आणली होती ती. इथं आणली होती केबल, त्याला टाकायला ते ऑडिओ.
माहिती माहिती माझ्या टेबलवरती पडलेलं
पटकन गाडी आहे का समोर VGA2 येते मग मागची डोर भाग करला
Check hello and testing.
Hello. Yeah. A very warm welcome to you all. I feel honored and privileged to welcome you to the 73rd CSIR-NCL Foundation Day celebration. May I now request Director CSIR-NCL Dr. Ashish Lely to address the gathering.
Professor Ajit Kembavi, Dr. Shivaram, Dr. Darbari, many dear colleagues and students present here, and my friends who are attending this event online. Very good morning to all of you, and a very happy new year. May this year be filled with happiness, good health, peace for all of you, and may this year bring you new aspirations, new goals, and new inspirations. I welcome you all today to this celebration event of our laboratory's 73rd Foundation Day. In a similar event last year, I had the opportunity to present before you a fresh roadmap for NCL for the 2020-2030 decade. You will remember that the roadmap was developed keeping in mind the key challenges and the new opportunities presented to the Indian chemical and allied industry in view of some of the important global megatrends such as climate change, sustainability, energy transition, supply chain disruption, force on self-reliance, emerging deep tech innovation ecosystem, and so on. The roadmap was based on the intrinsic strengths of the laboratory and our deep stakeholder connects. Over the past 1 year, we have identified and initiated a few large projects in these 7 thematic areas of our roadmap, and I'm happy to say that we have made considerable progress in each of these projects. And I would like today to give you a quick update on what we have achieved in the last 12 months. In the clean energy theme, we have launched a pan-CSIR hydrogen technology program with NCL as the nodal lab. At NCL, we are developing a few key technologies in all 3 parts of the hydrogen value chain, namely the production, storage, and utilization of hydrogen. And while we are further building on our past successes, such as the development of fuel cell and its demonstration in a bus, we have also initiated new projects in electrolysis, pyrolysis, gas, liquid, and solid forms of hydrogen storage. And additionally, NCL is deeply involved with the Pune Knowledge Cluster in conceptualizing India's first green hydrogen valley around the Pune area. We are also working closely with MNRE by providing important inputs for various policy papers which form the basis of the green hydrogen mission of the country. In the clean energy theme, we also completed technology transfer for the sodium-ion battery technology to our own startup, Rechargian, which has been incubated in the Venture Center. We wish the Rechargian team the very best, and we will continue to support them in their growth. Under the C1 chemistry theme, we have taken forward our DME process technology to the next level. We have installed a 100 liters per day lab scale continuous pilot plant for making DME. And we have also completed the development of basic engineering package for a 2.5 tons per day pilot plant, which we expect to come up in a suitable industrial premise. We are also planning an interesting collaboration with the Pune Knowledge Cluster, with CDAC and NSM for developing a digital twin for the DME pilot plant. And our distinguished speaker today is a strong supporter and collaborator of this initiative. In the circular economy theme, we have launched a mission program on chemical recycling of polyolefin-rich flexible waste plastics. NCL is again the nodal lab for this program, and we are involved in developing improved catalysts for pyrolysis as well as for depolymerization to higher value olefins. You may remember that we had developed a mechanical recycling technology for the PPE kits that were used extensively during the 3 COVID waves. We have now done preliminary work to show that the same know-how can be extended to the mechanical recycling of other non-woven products also, which remains an unmet need as of today. Under the theme of sustainable chemical industry, we have completed successful demonstration of a continuous pilot process for making bisphenol A and its downstream purification. The facility was inaugurated by the Honorable Minister of Science and Technology in August last year. We have also successfully completed development, demonstration and licensing of a novel process for continuous flow synthesis of azelaic acid. A few more similar processes were successfully demonstrated at POC level to various industry sponsors. There is an upsurge in demand from the specialty and fine chemicals industry for sustainable processes such as these, and I'm happy to say that the chemical engineering and the organic chemistry teams at NCL have joined hands to build on our strengths in this very important area. In the biotherapeutics team, we entered into an options agreement with a Bangalore-based company which is interested in taking forward our innovative work on the modulation of glycoforms of monoclonal antibodies. We have also completed major milestone in the National Biopharma Mission project for a particular biosimilar molecule and also completed several industrial projects in biosimilars. In the agri-tech theme, we have launched two very exciting programs, one on profiling of Indian honey, which has the potential to unlock massive exports, and the other on hybrid varieties of safflower that has significantly higher content of the healthier omega-9 fatty acids. In the biomass theme, we are working with major industries on lignin valorization, which is the need of the hour given the push for biomass-based technologies such as 2G ethanol and CBG that are produced in produce large quantities of lignin byproduct. Besides these technology-focused thematic project activities, all of you have continued to carry out high-quality, curiosity-driven research. You have published your work in international journals of great repute and also filed important patents. Several of you have delivered lectures and keynotes and plenary lectures in important conferences, and many of you have also taken up editorial responsibilities of widely read journals. So my congratulations to all of you. We are very proud of these achievements. Congratulations also to our Venture Center for becoming India's #1 bio-incubator. We are very grateful to the Venture Center for helping the Technology Entrepreneurship Club set up by our students for arranging industry visits and special training programs for them. Some of our own startups that were nurtured are nurtured in Venture Center and are doing exceptionally well, and I hope many more will emerge from the NCL Venture Center ecosystem. NCL's resource centers have made significant contributions during the past 1 year. The Technology Management Group was instrumental in interacting with more than 250 clients, signing 120 agreements, 5 licensing deals, 15 techno-commercial assessments, producing 11 technology and innovation digests, and also a report for the Pune Innovation Cluster on the potential for deploying CCUS technologies in the Pune metropolitan region. The Publication and Science Communication Group ensured that NCL was showcased through its digital formats and also in large number of exhibitions across India. The Laboratory Safety Group has worked diligently to ensure that the culture of safety percolates in the labs and that waste solvents and chemicals are stored safely and disposed of at regular intervals. I am happy to say that the fire safety training was not only imparted to all NCL residents but also offered to many other CSIR labs by our safety group representatives. The NCIM continues to offer high quality and professional services to the industry and helps earn significant ECF for NCL. The Central Analytical Facility is ready for launch, and we will hear more about it later today. The engineering services, admin, finance and accounts, stores and purchase have provided commendable support to NCL. We appreciate it, but we also expect even better support in 2023. I want to particularly appreciate the hard work done by the CNP team and many of my scientist colleagues for recruiting exceptional talent in NCL, which is absolutely crucial to securing our future. In 2021, NCL successfully organized 3 large conferences, the Macro 2022, the Bioprocessing India Conference, and the Student Annual Conference. Throughout 2022, we created the opportunity to listen to a large number of exciting lectures delivered by very distinguished speakers from across the world over a wide range of topics ranging from artificial intelligence to policy and strategy. We even organized symposiums and lectures to promote our Rajbhasha and regional language. I want to thank all the scientists and students who have worked hard to make these events very successful. So, what can we expect to achieve in 2023? The new year will certainly bring new opportunities for us, but it will also present new challenges that we must face. We are all working in an ecosystem that is constraining us more than ever before, and this is likely to continue in 2023 and might even increase. But we must never lose sight of our goals because the future only belongs to those who believe in the beauty of their dreams. We must keep our eyes on the stars and our feet on the ground. And we must not forget that our position in the science and technology ecosystem in India is unique and very important. We must retain and build on our identity. The expectations from us are high, and I have no doubt that we will work harder and perform even better despite all the challenges. So I once again wish all of you a very happy and productive new year, and I look forward to working closely with each one of you in 2023. Thank you and Jai Hind.
Yeah. Thank you, Ashish, for giving us a brief overview of the recent achievements of NCL. Now, our today's chief guest is Professor Ajit Khembawi. It's an honor to introduce him to this audience. Ajit Khembawi is an astronomer and a founding member of Inter-University Center for Astronomy and Astrophysics, which is well known to this audience. It's IUCAA in Pune. He is Professor Emeritus, former Director, and former Rajaramana Fellow of IUCAA. He did his PhD from TIFR with Professor Jayant Narlikar and was a postdoctoral fellow at Institute of Astronomy of the University of Cambridge. Professor Khembawi works on galaxies, quasars, and other extragalactic objects, various areas of high-energy astrophysics, X-ray and radio pulses, and the application of AI to astronomy and biology. He has published a large number of research papers and several books in English and Marathi. Professor Khembawi is one of the key persons responsible for India joining the 30-meter telescope TMT, and they have worked with Professor Ghez, who is a Nobel laureate, and also has taken up the LIGO India project. So he made sure that the LIGO India gets into the LIGO project. He has led the Virtual Observatory India project for 15 years, which has made important contribution to data management, analysis, visualization, and the development of tools for statistical analysis. He has headed a big data project supported by National Knowledge Network. Professor Khembawi is principal investigator of the recently launched Pune Knowledge Cluster, which brings together academia, R&D institutes, and industry to carry out capacity building programs and projects for the betterment of the city in the verticals of environment, health, electric mobility, and big data and AI. So you can see the breadth of, he's an astronomer, but he has worked on everything possible where statistical physics is applied. Professor Khembawi has been deeply involved with a large number of prestigious national and international bodies. Some of these include the Space Commission of the Government of India, ISRO Apex Science Board, the International Astronomical Union, the Astronomical Society of India, the International Virtual Observatory Alliance, and the Indian National Co-Data Committee. He is a fellow of the Indian Academy of Sciences and the National Academy of Science, India. I guess we can go on for another 10 minutes at least to tell you about his achievements, but without further ado, I'll request Professor Khembawi to deliver his lecture titled Galileo to James Webb Space Telescope, The Forward March of Astronomy. So, Professor Khembawi.
So good morning, namaskar.
It's a great honor and privilege for me to be invited to the Foundation Day talk of the National Chemical Laboratory. I mean, I don't know much about chemistry. Though in my school days, I used to always get more marks in chemistry than mathematics. And that is what I should have been doing. So, but I've been to NCL many times before. But I should say that in the last 6 months, I've been here more often than in the last 25 years. Because we have started a number of projects, as Dr. Lele briefly mentioned. And there are projects, there's a COVID data project which is going on, and the genome sequencing for COVID material. And then we are working on AI applications, digital twins, so on and so forth. And if the Hydrogen Valley goes forward, that will be a great project for us all to be invited. It's been very interesting for me to learn about the things which are being done in NCL at such close range, and I hope to continue that association in the future. Now I'm going to talk to you about how astronomy has moved forward from the time of Galileo Galilei. He first did his observations in 1609 to the present time. The James Webb Space Telescope was actually launched on Christmas Day 2021. So recently, a couple of months ago, Dr. Lele, Dr. Raja and I were in a car going to TCS, and at that time we happened to be talking about JWST, and then Dr. Lele suggested that I should come here and give a talk, but I did not know that it would translate into reality. Now when he sent me an invitation, I was aghast, simply because I don't know much about JWST at all. Okay, but then I took the opportunity to learn a little bit about it, and it's very, very exciting. But then I realized that in order for you to understand and appreciate the impact of JWST and the great progress which is made in fabricating it, launching it, we should know a little bit about prior astronomy too. So you set the basis and then you go on to what's happening today. Right, so now Galileo, you would all have heard about him. So he was a very great astronomer. So he did not invent the telescope. The telescope had been around as a curiosity, but Galileo first turned the telescope to the sky. So this was a 1-inch telescope. The instrument that he first used actually exists in the museum in Florence, and I've seen it. And then he used this, he had to hold it in the hand and look at the sky. But he made the most magnificent discoveries. And this, I believe, is the greatest example of what advances in technology can reveal to you about the universe. And until then, people had to be content with looking at just 4,000 or so stars that you can see in the night sky, and then the planets. And that was quite enough to do a lot of good work. And people even discovered here in India too about the precision of the axis of the Earth, just looking at the position of stars, which they had determined essentially by the naked eye. So, but when Galileo started using the telescope, then he made really startling discoveries. The easiest one is where he looked at the planet Jupiter and found that it had 4 satellites around it: Io, Europa, Ganymede, and Callisto. Now these satellites were going around Jupiter. That's why they are called satellites, and that made people very angry. Okay, not because Galileo had been going around, but because Galileo had discovered them. Because the idea was that everything should be going around the Earth, because the human being was there, and then nothing else in the world could be at the center of anything. So that was the theology at that time, and so people got really annoyed. But then Galileo continued with his discoveries. So what you see here are sunspots. And you don't know that these are sunspots because there's a great close-up there. And this created another problem because the sun was supposed to be completely perfect. The fact that there are spots on it and the fact that it's going around really, again, upset people. But his most elegant discovery made in those early days was the phases of the planet Venus. Because we always see Venus, it waxes and wanes, but what we see is the changing light from it. You have to see it early in the morning or late in the evening, just after sunset or just before sunrise. But if you look at it with the small telescope that Galileo used, you see that it is changing its phase, as the moon changes its phase. So what is the implication of that? So you see here the phases of Venus taken from a small modern telescope, and then you see that it goes from being almost full when the disk is the smallest, okay, to the large thing, the large crescent there. So you can see the same thing in this original diagram by Galileo. Okay, so you can see this important thing that when it's a crescent it is larger and when it is full it is smaller. So at that time everybody believed that the whole universe goes around the earth, the geocentric theory. But Galileo was able to demonstrate that that is not possible. If Venus and Sun were both going around the Sun, going around the earth, then the phases would not be possible. And he argued very convincingly that for that Venus and Earth have to go around the Sun, which was the heliocentric theory, which had first been given by Copernicus, much before the time of Galileo. And you all know that Galileo was punished for making all these wonderful discoveries. He was a truly multifaceted person. So to make his living, I mean, unfortunately in those days you couldn't become a scientist who was paid by the government. Occasionally the king or the emperor gave you some money, but Galileo made his living by giving tuitions. He must have been pretty good at it. Okay, then he was a great expert on military projectiles, right? Because big guns were being invented at that time, and then you have to see where you should point in order that the shell lands where you want it to go. So he established that the trajectory is parabolic. But he was also a great theoretical physicist, even though he did not have the mathematical apparatus which later Newton created and other people created. So, but Galileo gave what is known as the principle of inertia, and that became the basis of Einstein's special theory of relativity. He also went up, I mean, I don't know whether this is true, but he dropped a light and a heavy object from the Tower of Pisa and they both fell with the same velocity. So then that is what's called a principle of equivalence by Einstein, and it was the basis of the general theory of relativity. Okay, so Galileo was truly phenomenal. So then we start with a 1-inch telescope in 1609 which was used, and then people started making bigger and bigger telescopes, and one of the record-breaking telescopes was here by William Herschel. So this telescope has a 48-inch diameter. So you've got the primary mirror, then you'll have the secondary mirrors for focusing and so forth. And what is most important is what is the area of the primary mirror, because the bigger the area, the more is the light which is collected. So so then William Herschel built this telescope. You see, it's quite a difficult construction, quite ungainly, but you have got these wheels here, and it can also swing on the other axis. This is what is called an altazimuth mount, and therefore you could point the telescope to nearly any direction that you want to. But you see that there were no instruments at that time, so one had to observe the sky with the naked eye, and therefore the astronomer had to sit in a stand here and then take a look at what was happening inside. So, so now this was again what's called a refracting telescope. So Galileo's telescope had two lenses. This also had two or more lenses. It's a refracting telescope. It was the biggest telescope in the world for over 50 years. But it was located in this place called Slav, which is close to London and near the airport. And that is not a very nice place to observe from, because there are a lot of clouds all the time. In fact, it used to be a big joke that had reduced a little bit the cloud and the fog. And because of all that, not much was done using this telescope. Herschel himself made very great discoveries, including the discovery of the planet Uranus, which was the first non-naked eye planet to be discovered, even though other people had seen it before without realizing that it's a planet. And Herschel also first mapped the shape of a galaxy. He got it wrong by putting the Earth at the center of the Sun at the center of the galaxy, but that happened because he was not aware that there is dust in the galaxy which obscures the distant stars. Right? So, but this was a record-breaking telescope. There are other bigger telescopes made at that time, but then people went to fundamentally different telescopes. But before I continue with this story, let's look at the electromagnetic spectrum. So when we are talking of observing through a telescope, people always imagine that you are looking at light which is visible to the eye. which was true for a very long time. But now the entire electromagnetic spectrum can be detected, because you first have, here is a small optical band, on two sides of it is the near infrared, mid infrared and infrared band, then the ultraviolet band. And then you have got on the high energy side, you have got the X-rays, and you can go right up to TeV gamma rays. Okay, so the typical energy of a photon here would be 1 electron volt or less, whereas here it would be, you can say 20 TeV. So there's an immense factor in the energy of the photon. But if you come to the low energy side, you go to microwaves and then radio waves. And these are very, very low energy photons. Right, so now only this band was known to us for a long time. But then around the Second World War, people first started, they used the radar dishes to detect emissions from the sun, and radio astronomy was born. And then X-rays had to wait until we could fly detectors outside the Earth's atmosphere. So these are all young astronomy is about 50, 60, 70 years old, but they are extremely important because there is some kind of principle of equivalence, meaning that equipartition principle, meaning that if you look at a star, it mainly emits in the optical, infrared and ultraviolet bands. But if you look at active objects, meaning a quasar for example, or an active galaxy, what they emit almost equal energy in any one of these bands. Okay, except that here the number of photons would be extremely large because each photon is of very low energy, and here the number of photons is very small. But the importance of each band to the fundamental structure of the object is the same entirely across the spectrum. So now if you observe in all these, then you do what is known as multi-wavelength astronomy. You cannot understand the physics of an astronomical source if you confine yourself to optical wavelengths. So this is a very familiar picture. I'm sure many of you have seen it. It is known as the Crab Nebula, first discovered by Chinese astronomers. Everybody saw it, but Chinese astronomers made a careful note. In the year 1054 AD, a big star here at the center exploded as a supernova, and what you see here is a supernova remnant. Okay, and at the center there is a pulsar. So you see here now this is visible infrared, radio, ultraviolet, X-rays and gamma rays. So you see different representation of the objects here, and all this data is necessary to get a holistic idea of what this object is. But now there is a further development. These are all electromagnetic waves, but in 2015, for the first time, gravitational waves were actually detected. The existence of gravitational waves had been established before that, but the actual detection using a detector, just like I detect optical photons or radio photons, was made for the first time in 2015. So as a result of which you have got multi-messenger astronomy plus gravitational waves, and so this together is called multi-messenger astronomy. It's not multi-wavelength astronomy. Right, so what is the difficulty in observing the electromagnetic spectrum? The difficulty is mainly created by the atmosphere of the Earth. Right, so you look at it this way, that you can see the absorption here. So you have got the optical band going in, reaching us with some extinction, and that is why we have evolved so that our eyes can detect the optical radiation. And then when you come here to very small short wavelength, the complete 100% absorption is there. Again, at very short wavelength, 100% absorption. But radio waves can reach us on the Earth. So which would mean that if you want to observe at infrared, ultraviolet and the higher energies, then you necessarily need to have an observatory outside. So what people first did was to started flying balloons with instruments mounted on them, and then astronomers used rockets, and then after that they finally built satellites which could go into orbit and stay there for a very long time. And the James Webb Telescope is a great example of such a satellite observatory, which I'll come to at the end of my talk. So then what are the tools of an astronomer? I don't mean in terms of the instruments actually. I'll be talking about some instruments a little bit now and then. But you see that we do imaging. So you get an image and you process the image, and then I showed you the images of the Crab Nebula. then you can do photometry of the image, meaning how much light is coming in broad bands. Okay, so let us say that around 5000 angstrom, 6000 angstrom, 7000 angstrom, like that, or in one of the other wavelengths which are accessible to us. Now, photometry can also be done on point-like objects, meaning a star, a typical star in the sky is very far away. It has got a size like the size of the sun, and so it is essentially a point object, but it gets spread out a little bit because of the atmosphere, and you can do photometry on that. Then of course there is spectroscopy, where we use very high resolution spectrographs to make detailed spectroscopic measurements. There can be polarimetry, where you look at the polarization, which tells you about the scattering which takes place there, the presence of dust and so forth. And then we have got variability studies, which are extremely important. Okay, so in fact now much of astronomy is devoted to looking at how objects vary. The variation can be very simple. It can be because there are two stars in a binary system which obscure each other from time to time, which leads to variability. It can be a tiny exoplanet, okay, which goes across the disk of its parent star, and then there is a very small dip in the intensity from the star. Or it can be a star which is pulsating, or it can be the region around a supermassive black hole, okay, which is varying. So, and it could be a supernova which suddenly goes off. So, there are complete surveys which are dedicated to look at variability. So, what you do is that you take a wide field camera and then you keep scanning the sky multiple times a night, multiple times a month, multiple times a year, and so forth. And then you quickly compare results to get variability, objects which vary on different scale. So, there are really marvelous surveys totally dedicated to find objects which are variable. Right, so now a quick thing on astronomy facilities available in India which cover the electromagnetic spectrum. Two outstandingly successful telescopes. The GMRT, the center for which is the NCRA, which is based here in Pune, and that was one of the main reasons why Professor Nalekar decided to bring Ayuka to Pune, because the GMRT was coming up at that time. It's in Narayangaon. And then there's AstroSat, which is a multi-wavelength observatory. Its main thing is the X-rays, but it observes in ultraviolet and observes also in the optical. And this has again been outstandingly successful. Okay, so then there's Aditya L1. It's at a Lagrangian point. I'll come to that later. And Aditya is going to be launched later this year. Right, and then we are going to very large projects, the 30-meter telescope, and then the LIGO detector, and then the square kilometer array. So this is going to be in India, the third LIGO detector, and India is a major partner in these two mega projects. Now, I unfortunately will not be able to talk of most of these things today. Okay, then now let's come back to telescopes. And my talk is mainly going to be driven by the development of telescope technology. And then I'll give you very small, just a couple of examples of outstanding results which have been obtained with this telescope, which are profoundly important, but also which are easy to understand. Okay, so then a modern telescope is first of all a reflecting telescope. That is because making a large lens the lenses are very heavy, difficult to make, and then they are long focal length necessarily, and also they produce distortions, optical distortions. So what you do is that you use a mirror. It can be a paraboloid, a hyperbola, all sorts of different shapes, and light comes from a distant object, parallel rays, and they come to focus at one point. So you put your eye there and you can see it. Right, but then when you go to the next level of the telescope, first of all, what happens is that there is a mirror here, the primary mirror, and then here you have got a secondary mirror. So the light comes in, is reflected by the primary mirror. So the area of this mirror is very important for saying how much light can you collect. It goes to the secondary mirror, then goes down, goes through a hole in the primary mirror, and is detected by an instrument. Right, so you see, now here there can be any number of variations of the path of the light here. And then you need a mechanical movement, electromechanical movement, to track an object. Because the earth is rotating, so the object will move in the sky, and then you need to track it. Okay, so you point a telescope to an object, it should remain on that object for a long time. Because our eye has got about a millimeter diameter, and then we can integrate light for 1/10 of a second. Okay, so here you have got mirrors of many meters in diameter, we'll see. Okay, so you take 1 meter by 1 millimeter and square it, and that would be the extra collecting power that you get. And then you can integrate for very long periods of time. On the earth, you can integrate a few hours until night, but if you are in space, you can integrate continuously for years. Right, so one such telescope, it belongs to the Indian Institute of Astrophysics. It's in a very remote area of Ladakh called Hamle, quite far from Leh, and it's a small telescope, 2-meter telescope, and you can see the reflecting telescope here. It has done extremely well. You need to put a telescope in a site like Ladakh because the air is very dry there, and then therefore you can do near infrared observing. Okay, and then you need dark nights, you need clear nights, you need a large number of clear nights, and all these conditions are satisfied in Ladakh. Going there, of course, is extremely difficult, but over a period of time, a very nice observatory has been developed there, where other institutes too have put their own telescopes. Now, this telescope is again, people of my generation, when we are reading books, we are told that Palomar 5-meter telescope, it's a 200-inch telescope actually, and this is the biggest telescope in the world. It was the biggest telescope for a very long time, and very nice, very great discoveries are made with it. So, in addition to saying that it's the biggest telescope, then it was also said that no bigger telescope can be made. And they are the reason for that. It was not completely ego. Then the Russians made a 6-meter telescope, but it really didn't work too well. Okay, not like the Palomar telescope. Right. So then you see, it has got a 5.1 diameter, and then the weight is 14.5 tons, and that is the deciding reason why they said you can't make bigger telescopes. And then it was made of Corning Pyrex glass. So you can imagine a 5 meters is from there to there, and then you have got to make a mirror like that, and then you need to polish it, and you need the accuracy which is needed is 20-30 angstroms. Okay. So that's the kind of accuracy, and something goes wrong with it, breaks at one point, it's completely gone. Right, and then you coat it with silver coating is there, and that is the reflecting coating. The glass itself is not reflecting; it's a coating which is reflecting. And then you have to hold it there, and you have to turn it to any point which is necessary and hold it at that point. So it's a technology. This is a very vast telescope if you look at the stand and look at the great big dome there. But then this business of never being able to make a bigger telescope, clearly that is not the way technology and science go, and there are always progresses. Right? So now first let's think of what can you do with a bigger telescope. There's a student of mine called Lakshmikant Chowre from Chhattisgarh, a very remote area. He was a great expert in very fine and detailed analysis of astronomical images. And you see that this is taken with a 2-meter telescope with a 54-second exposure, and this is with a Palomar 5-meter with a 1.6-hour exposure. So there's really no comparison between there and there. And then so what is the net gain? So here we have plotted the intensity across this galaxy, meaning the intensity is highest in the center. It decreases as you move over the face of the galaxy. And with the Sloan survey, you see, you can reach up to this point because there is always a background light in the sky. Like Panchoti, for example, you can't see anything at all. And in addition to the light, when I stand in the gallery of my house to try to look at the sky, there are trees all over. The trees are wonderful, but they don't let you look at stars. Okay, so, but if you put off all the lights in the city, you'll get a black sky, but there'll be a glow due to the atmosphere. But when you go out, when you go into space, there's almost going to be an irreducible goal. You can never reduce it. And what is that due to? It is the net contribution of the many billions and billions of galaxies in the universe. It's hard to believe, but that is true. And then you see, so you have to see how much above this background sky you can go. Now here, using this data, you could go to 5% of the sky. But the analysis which are done by Lakshmikant, it takes you 0.1% of the sky. So if there are 10,000 photons from the sky, there will be just one photon, which is a signal photon. So that is the kind of counting that you need to do. Right, so now here are the new generation telescopes. So this is called a very large telescope. So it belongs to the European Southern Observatory. It is there in Cerro Paranal in the Andean mountains in Chile. And so there are 4 telescopes, and you see that they are in a perfect line. And they are identical because what happens is that you could use them as 4 different instruments, or you could collect the light from all of them and combine it together, or you can also use it as an interferometer. Okay, that is why they put the telescopes there. And then these are their names, this means the moon and so on. Then what is the diameter of the mirror? So you see the 8.2 meters. So you are left 5 meters diameter behind. Right, so, and then how did you manage it? You managed it by using a glass ceramic Zerodur. You will know much more about this than I do, but this is light material and you can make the mirror thin. And so the weight of the mirror is 23 meters. But the Palomar mirror weighed 15 meters. But here this is 1.6 times bigger in diameter, meaning 2.5 times bigger in area. Okay, so therefore this should weigh much more, but modern technology which managed to do it. Okay, this telescope has made incredible contributions which I'll come to soon. But then can I build even bigger telescopes? Can I build a 20-meter telescope with this kind of technology? What are the problems there? The mirror blanks is very expensive and hard to find. Then probability of breakage increases. The support systems cause large optical deflections, large deformations, and you require very large vacuum chambers and so forth. It all becomes untenable. You cannot build bigger telescopes. And so how do we move forward? The way forward is to break the mirror up into small mirrors. So you take a lot of mirrors and then you stick them together. Okay, so you see that here is a very nice picture of one of the VLT mirrors being moved, and you must appreciate the fact that this has to go to very remote locations at the top of a mountain. Okay, so that becomes, this simple practical problem becomes insurmountable many times. Okay, you can imagine how the 2-meter mirror was taken to Hanley. Right, so now we come to the era of segmented telescopes. Right, so you see that this is the best performing segmented telescope. It is not a Keck telescope. There are 2 of them. They belong to to Caltech and the University of California system, but people from all over the world can apply for time on it. But mainly their telescope. There are 2 of them there, and for reasons which I have already described, and they are located here. There are many telescopes. So this is in Hawaii, and again you see that the ideal spot to have a telescope is you go to a large ocean. The Pacific Ocean is very large, and then you have a small island on it, like the islands in Hawaii, and then you need a mountain there. Okay, because for the stability of atmosphere, which is very important, these are the best possible things. And this Mauna Kea volcano, extinct volcano, satisfies all these conditions, so it is there. And so the idea is also to put the 30-meter telescope there. But as some of you may have heard, it has run into a great problem. Because there is divinity associated with this telescope, it's sacred to the Hawaiian population, and that has led to a lot of problems. So let us look at the segmented mirror here. You see that this mirror is 10 meters in diameter from end to end. It is not round, it is a sort of hexagonal in shape, and this is one person stretching arms there, so you can see how big it is. And here are the segments there. Okay, so you see that you've got 36 hexagonal segments. So why hexagonal? That is because you can fit them together and you can get a nearly round shape. I mean, it's a detailed consideration which says that hexagons are the best. And then you see each is a 1.8 mirror, 1.8 meter mirror, meaning each is the Hanley telescope is 2 meters. So each segment is as much as the Hanley telescope, and it is 36 pieces are there. Total diameter is 10 meters. Okay, so you see that what you require here is that now the whole thing becomes parabolic in shape, and then you have you need to hold the mirror in shape all the time. And that is done by having sensors below each mirror, which senses the shape of the mirror every second and connects it. And so this is done, this is what is known as active optics. Okay, meaning that the mirror, so you keep taking a standard image, look at how the image is being distorted, and then you use active optics to correct it. And in fact, such correctors are also used on the large single mirror of the very large telescope. Okay, so you need these correctors and pushing and pulling the thing. And then you see systems, these are the active optics, and so the accuracy is to within 4 nanometers overall. So you require extremely fine accuracy, and then images are sharpened with adaptive optics. I'll come to that in a moment. So what is adaptive optics here? Is that if you look at a star, you see the sun has got a diameter of 700,000 kilometers. Okay, and then so if you put it at the distance of the nearest star, which is a couple of light years, then its diameter, the size of the image will be virtually zero. But if you look at Alpha Centauri, Proxima Centauri, which is the nearest star like the sun, and then you will find that its image actually is about 1 arc second across. And that is because of the atmosphere. As light passes through the atmosphere, it sees a refractive index, a refracting medium. And that medium is changing continuously. Okay, it tells you in seconds. And because of that, a light ray keeps getting deflected. Which is why when you look at a star, you see it twinkling. Because the light sometimes enters your eye and sometimes it doesn't enter your eye. But planets don't twinkle. And that is because they have got a finite disk. Right? So the distortions get averaged out. Right? So now, because of that, you see this twinkling there, and you want to reduce the size of the image as much as possible. Because when you reduce the size of the image, you have two great advantages. One is that your resolving power increases, your resolution increases. So for example, two stars, binary stars which are very close together, could be distinguished as two separate objects rather than one merged object. Number one. Number two is that there's always the background, and the bigger your image is, the photons from the object are competing with background photons coming from the same area. So you need to make it as small as possible. Right? And so I showed you this thing about the Palomar telescope, how important it is to go below the background, and that is why we want to reduce the size of the image. And how do you do that? And you do it using a technique which is known as adaptive optics. You could also do this in the image processing, and we have been doing a project on that, how to do it in image processing. But what you do is that you shoot a laser beam up to the sky, and it creates an artificial star in the atmosphere, and then that is very close by, and then you keep seeing that star, and you see what distortion is produced. And then one of the mirrors in the path of the light ray is a deformable mirror, and that mirror goes on deforming in such a way that the distortion in the artificial star is reduced to an absolute minimum. And so that requires a frequency of about 1,000 times, the correction to be made 1,000 times a second. And when you do that, then you apply that correction to actual stars that you see, then you see that instead of seeing a light like this, you'll see it beautifully peaked. And this is known as adaptive optics. So this is a field without adaptive optics, and the same field with adaptive optics, and you see how the stars are standing out. So this is an incredibly important technique. So far it has been used after you build the telescope, but the new telescopes which are being built adopt this right from the beginning. Right, so here this is a laser beam going up to create the sky. So what I will do now is to give you a very quick introduction to the thing about a very beautiful experiment which was carried out over a period of 20 years by two groups, Genzel and Ghez, and they got the Nobel Prize in 2020, which they shared with Roger Penrose for his discovery of black holes. So these people established that it is extremely likely that there is a supermassive black hole at the center of a galaxy. So how do they do that? So you see that this is a Milky Way galaxy, and you can actually see it. I grew up in Hubli, and there I could see it every day. Okay, so nowadays you can't see it because of the excessive light. But if you go to a darker location, you can immediately see it. Right, and then if you take, this is a pan image of this galaxy, and then if you look at that, you know it's very thin here. There's a thin disk, there are spiral arms in the disk, and this is a bulge. Right, so when astronomers, radio astronomers made a measurement of the center of it, they could reach the center. Optically, you can't reach the center because each individual star becomes very faint. And in addition to that, there's a lot of dust in the plane of the galaxy, right? So which you can see here as a brown thing, and which obscures the star. But radio astronomers have no such problems, and they discovered a source which is known as Sagittarius A, and in that there was a component called Sagittarius A star, and which are extremely compact and which appear to be stationary, and that is taken to be the center of the galaxy. And then the point is that there is evidence that there is a supermassive black hole. Supermassive meaning 1,000,000 times or more the mass of the sun at the center of many galaxies. So the question is there such a supermassive black hole in the center of a galaxy? And there are many ways in which you could indirectly infer it, but if I want to do it absolutely directly, then I must look at the motion of the stars around the center and see how these motions are perturbed. Right, so that will become very clear here. So you see that you have to go to the center of the galaxy, and how do you reach it? First of all, you use near infrared astronomy, okay, because there the obscuration due to the dust is minimum. Second, you use very large telescopes, so they use the VLT and the Keck, and then you also use adaptive optics, and there's a similar technique called speckle interferometry. So doing that, you see that they have got what the scale of this? This is about 3 light months. And what is the scale of the galaxy? It's 100,000 light years. Okay, so you have gone to 1/200th of the region of the galaxy. Okay, and then you go further, and here is Sagittarius A star, and these are stars close to Sagittarius A star. And then you observe them. And there's a particular star called S2 here, and this is the center of the galaxy. And what we want to do is to measure the motion of the star. You measure all the stars, but this is the closest to the center, and you measure it. Okay, and what was established is that you see that the orbit of S2, you see that it is like an ellipse, and this is the closest approach, right? But look at the plot here. It is indescribably beautiful, right? You see that this began, they started in 1992, and then they continued here. They reached here in 2002, and on the basis of this they could come to a very fine conclusion, but later on in 2010 you see that they got back. It's a beautiful ellipse, and this is no different from what Kepler did in the 17th century, because he was given data by Tycho Brahe, and Tycho Brahe gave it to him because he thought he's a bright student. Let me give him a very difficult data so he doesn't do too well. Okay, and then, but it happened to be the data on the orbit of Mars, and then Kepler realized that it's an ellipse. It took him a very long time, 20 years to establish that it's an ellipse, but then he gave his famous laws. And what did he say? He says that Mars goes round the sun in an ellipse, and the sun is at one focus. And that is exactly been proved by modern technology. And you see that Sagittarius A star is at one focus, and then you've got this ellipse. And the blue and the red are because of two different groups, the two groups who got the Nobel Prize. Okay, so they're completely independent observations, completely independent analysis. And then you see what is the mass of this object. Kepler couldn't find that out, because that was established because you have to wait until Newton's law of gravitation. And then we know that the mass is 4 million times the mass of the sun. So there's an object here. Look at another very nice thing. You see here, this overlap region here, and you find that the overlap is not perfect. So you may imagine that the accuracy actually is much greater than the size of the dots. And so the fact that the overlap is not perfect it's a real effect. And what is it due to? It was believed that it is due to the small motion of Sagittarius A star. Because if it moves, then the ellipse will get affected. But the real explanation is much more dramatic. So there's in 2020, there's a new experiment called gravity, which uses light from the 4 VLT telescopes. Okay, and what they established is that the ellipse is not perfect because the ellipse is actually swinging in space. So if you do this over a couple of 100 years, this is what you will find, the ellipse is swinging in place. And the precision per orbit, the orbit is 16 years, is 12 arc minutes. And what is it due to? It is due to a general relativistic effect. When Einstein gave his general relativity theory, he said there was a slight precision in the orbit of Mercury, which could not be explained by anything known at that time. And that residual was fully explained by Einstein's theory of gravity without introducing any new constant in the theory. And that was considered to be a great triumph, and it's exactly the same effect. So, so you see that what you require is very phenomenal accuracy, because how do you actually measure the position of stars over a 20-year period? What is the coordinate system? So that is very difficult. Okay, here is a 30-meter telescope which is being built. I mean, it has not yet started being built because of political problems, but India is an important partner here, and we have made various things. All the active optics is being made in India, plus mirror polishing of many segments is also happening in India. Okay, now astronomy from space, I'll run through the Hubble Space Telescope, but I got about 5-10 minutes. Oh, is that okay? Yeah. Okay, all right. So, so you see that why do we need telescopes in space? It's because of atmospheric absorption. I've already talked about it, atmospheric blurring, and the need to do continuous observations. And so the first space telescope, I mean that everybody knows about, there are many more in different wavelengths. This is optical ultraviolet, is the Hubble Space Telescope. Okay, and then it was launched on April 24, 1990. It has got a mirror 2.4 meters in diameter, and it's in near Earth orbit, only 535 kilometers altitude. And Hubble, and you see here the number of observations made by it. Oh, my pointer is gone. Okay, doesn't matter. Number of observations made by it is 1.5 million, and the number of research papers written by it is more than 19,000. So clearly, this is a very very successful experiment. And you see, for example, this is an object which is known as a globular cluster, which can have 500,000 stars. And then this is a ground-based image. But if you do look at it with a space telescope, then you see that it gets expanded, and then the circle that you see, each circle encloses a white dwarf. Right, and this is a picture which is known as the Hubble Extreme Deep Field. So what you do is that you take a tiny part of the sky, and then you go on observing it today, tomorrow, day after tomorrow, next year, and then you combine them all to get an ultra deep exposure. So the exposure of 2 million seconds. And there are only 2 stars here as far as I can see. Every other thing, including the tiniest dot there, okay, is a galaxy. So if you look at one very tiny dot, then it would have typically 10 raised to 11 stars. Okay, so then out of that we know that there is at least one planet around each star. So 10 to the 11 planets. So even if there is a 10 to the -7 probability of the planet having life on it, that 10,000, 100,000 life forms are in one tiny dot. Okay? And so there are about 55,000 galaxies there. This is a much shallower field, and you see those dots there. Again, it's very nice to zoom into them and see that every knot, how it expands to be a galaxy. Right? And then now I come to the last part of my talk, the James Webb Telescope. So the Hubble Space Telescope could observe in the optical, infrared and ultraviolet. The James Webb Telescope is limited entirely to infrared. So instead of having 4 different cameras, it has got 4 different cameras, but all of them concentrating on near to mid infrared. And you'll see why this is so important. So here's a picture of the telescope, and then you see that Hubble Space Telescope has 2 meter diameter, and the primary mirror here is 6.5 meter diameter. So these are again segmented mirrors, and they are gold plated. They are gold plated because the reflectivity in the infrared is the best there. And then you see, launching this kind of a thing is not very easy. So what they did was that they packed it all together, like packing things in a suitcase, and then you go to your destination and you unpack the suitcase. And it was unpacked. So starting their launch from the Earth, and this was on Christmas Day, 2021, and then you see that gradually it is being unfolded, the whole telescope. There are thousands of high risk maneuvers were involved in unfolding it. Okay, and then it unfolded in 9 days, it unfolded completely. And every one of them obviously was successful. And where is the telescope? It is not going on the Earth. It is at a special point called L2. So if you look at the Earth-Moon system, the Earth-Sun system, and both are going around each other, if you take into account the attraction of the two bodies, plus the centrifugal force because of the rotation, then you get 5 special points. And then L1 is very important, and L2. The thing about L2 is that if you keep an object at L2, it will stay at L2. So just imagine, you put a telescope there and point it to the sun, or point it to the Earth. Okay, then it will always remain pointed to the Earth. All that you need to do is to turn it around slowly, just as the two bodies go around each other. But in a frame in which the two bodies are at rest, the telescope is not completely at rest, it goes down in an ellipse around L2. L2 is an empty point, there is nothing at L2. But the gravitational potential there goes like that. Okay, so it took 29 days to reach L2, and L2 is at 1.5 million kilometers from us. Okay, so you see, there is a amazing thing which you need to do, is that one side of it points to the sun. And because it is 1.5 million kilometers away, it has got, the temperature there can be held at about 85 degrees. But the temperature you need for the near infrared detectors is minus 230 degrees Celsius. Right? So there is a wonderful heat shield, and then it took a long time. It took 6 months to cool that side to this temperature, and then the observations began. Okay, so you see there are these 4 instruments there, and they all work in the near infrared, and they all kinds of, they can do imaging, they can do spectroscopy, they can do coronagraphy, all the techniques that I mentioned. And you see that, look at this unbelievable picture here. So this one is it is a panchromatic picture, meaning different bands of the infrared. And what you see here are dust clouds. So there are in the galaxy dust clouds everywhere. And then these dust clouds are where stars are born. And then you can see these individual stars there. And then, so this is in the mid-infrared, and this is near-infrared. And here you can see the picture by Hubble. When the Hubble picture was obtained, it was a staggeringly good picture. But now compare the Hubble image with this image here, and you'll see what is the improvement in the thing. The problem with analyzing this kind of a detail is that you will require very detailed hydro codes to do it. And that is where Dr. Darbari comes into the picture, okay? Because he is the head of the National Supercomputing Mission, and so all of us are going after him to say, "Hame bhi thoda time de do," on the supercomputing mission, right? And here is a pair of interacting galaxies, right? So these are merging galaxies. They are got into each other. They are 2 spirals, which eventually may become an elliptical galaxy. And then you can see those tiny dots that you see are star-forming regions. So here is a Hubble picture of the same object, and there on the right is a picture taken from the ground. So you see the importance of going. That picture, of course, is not as bad as it looks, because when you do the image analysis, you can get much more detail. But you can see how life is different when you go from the ground-based image to the Hubble Space Telescope to this one. And the last one I'm going to show you is that this one here, this is not a real, it's a simulated image. This is a star, it's a G-type star like the sun, and this is an exoplanet. Okay, these are actual planets going on the sun, but not a real image of the planet. And you see that this is about 0.3 times the mass of Jupiter. But Jupiter is far away from the Sun. But this is very close to the Sun, so it has got an orbital period of only 4 days, 4.1 days, which goes around the Sun. Now, the thing is that as the planet goes across the face of the star, there is the atmosphere of the planet which you see in blue. So the light of the star passes through the atmosphere, and then the spectrographs on the thing can provide you with a spectrum of the atmosphere. Okay, and then you see this beautiful spectrum here. And what do you see? Sodium, water, carbon monoxide, carbon dioxide, and there's sulfur dioxide. And I'm not an expert on this, but I read that this is the first detection of sulfur dioxide. And sulfur dioxide requires photoprocesses in order to produce it. Okay, so which tells you a great deal about the chemistry which goes on in the planetary atmosphere. And here I've just shown a spectrum in a different area, so you can see the presence of potassium. Okay, and then the point is that SO2 is detected for the first time, and then in order to have the kind of sulfur there, you require the accretion of small planet-like bodies onto it to form the big body. And the abundance of oxygen indicates that the exoplanet initially formed far away from the central thing. So you see, now this is just a thing which says that why do people do astronomy? They do it for many reasons. It gets interesting, I get a job, I fell into it accidentally, all sorts of things. Okay, but sometime, somewhere, people remember driving towards the truth, so I put this thing from the Ishopanishad. But the thing is that the exoplanets that we have seen so far are completely abnormal. Because in order to see an exoplanet, you have to see the effect it has on the star. So the Earth, Mercury will have a very small effect on the star. But if you had Jupiter, which moved close to the Sun, it would have a great deal of effect. It would perturb the star. And that perturbation you can see in the spectrum of the star. Or it can go across the star and produce an eclipse, and that is how you detect it. So the exoplanets that we are detecting now are very large planets which are very close to the star. Whereas our solar system is not like that. But we have detected many Earth-like planets. And it's quite possible that there's life on them. Because the Earth-like planets, meaning that they're the same size, they're the same distance from the star, which is more like the Sun and so forth. So these are very exciting times. I'll end here with just one thing, that through the Pune Knowledge Cluster, we are conducting a course on exoplanets. Okay, and we have advertised it, but I'm again advertising it here. It's going to start in February. It's going to be conducted, it is curated by Dr. Ravi Koparoppu, who used to work, who works in NASA, and is a great expert on exoplanets. So there will be people from India and from the US who will be giving these talks. And we are designing the course to make it interdisciplinary, because this is not something which is limited to astronomy. And astronomers have now given up. We're talking of spectra, carbon dioxide and so forth. Okay, so if any one of you is interested, please do apply to it. And it's there, you'll find it there on the PKC site. And you'll find it a very interesting course. And you may start doing research in it. Thank you very much.
Thank you, Ajit, for this amazing journey. It was like a sci-fi journey for us here. Now the floor is open to questions. You're okay to take?
Yes, absolutely.
Yeah. So.
Yeah, I can see you.
Thanks, Ajit. This was a fascinating talk, and it's really exciting to know that there is a probability of life on other paths in space. So I was just wondering whether you could elaborate a little on the developments in astrobiology that are trying to, bring evidence to this hypothesis.
Yeah, see, I unfortunately don't know much about astrobiology. The point is that when you learn to detect these molecules, so why did we go here in the near infrared? Because when you have got these molecules, their lines should be in the infrared. So that is what you have done. We are learning to not only detect them, but also to interpret them. And so the idea is that you'll detect things which are essential signatures of life forms. Right? So, and the one signature that I know about is that if you look at the ratio of methane to carbon, methane to oxygen, methane to carbon dioxide and so forth, if it is in certain areas, then it means that it has essentially been due to life forms. Okay, so you need to do quite a lot of that, and that is why, first of all, this is there. There are other such missions also dedicated to observing planetary atmospheres. There is very little work on that done in India, and which is why we are conducting this course and provoking this thought.
Yeah, I had a question about the L2 that you showed.
Yes.
There were some other points, L1,
Yes.
L3. Are they also points where things would be stationary? Or
So the easiest to understand is L1. Okay, so so just imagine an object which is a little bit away from L1. Okay, then it is being pulled by the sun in one direction, the earth in the other direction, and you could imagine that there's a point where the two forces are equal, but there's also the centrifugal force because of the motion of the earth around the sun. The three together at that point, they are equal. So it becomes a point where if you keep an object there, then it will remain stationary. Stationary not in space, but if you draw a line joining center of the sun to the center of the earth, okay, then this point will be there. And in the rotating frame, it will be stationary. Now, if I put a stone there and then I move it slightly towards the sun, it will go into orbit around the sun. Slightly towards the earth, it goes orbit around the earth. So the idea is that when a sun becomes a red giant, which it will do one day or the other, and then it will expand, it will fill the Roche lobe. It's called a Roche lobe. And the matter which touches the L1, it's like a pichkari, you see. So it gets shot towards the sun and then goes on to it. So this is a very important point for the evolution of stars. Okay, so L1 is like that, and these 5 points all have minima there in the potential. Okay, and L4 and L5 are the best. Okay, because they are stable minima. So that is why you put a thing there, spacecraft there, it just keeps going in an elliptical orbit around. But you can't have that at L1.
Right. Can I ask one more question? This is maybe probably a stupid question, but why is it that all the orbits are elliptical? The sun goes around the center of the galaxy in an ellipsis.
Yes.
Everything else you showed, it's always elliptical. Why is that?
So it is not at all a stupid question. I mean, it's a very important question. Kepler knew it's an elliptical orbit. He didn't know why. Look at it this way: if you the Earth is going around the sun. Okay, so there is the attraction because of the sun. Forget that the Earth has a mass; it's just a test particle, and then there's a centrifugal force. If you look at the net potential due to this, then you see that the potential at infinity is 0, and when you come down, the potential goes down like this, and then it shoots up. Okay, so what happens is that you get a well like this. So if you are at the bottom of the well, okay, then it's a circular orbit. But if you have got a little bit more, the same angular momentum, but a little bit more energy than the bottom, then you go like this in the potential. It's at a potential well, so you go like that, and that's an elliptical orbit. But if you go to general relativity, the potential goes down, goes up, and goes down again. Okay, and because of that, you get black holes. So it's elliptical orbits are there because of the angular momentum.
Ajit, fascinating. Tell me, with all these space observatories now, what is the relevance of a terrestrial observatory?
Oh, the terrestrial observatory, because you can make bigger and bigger telescopes. Okay, so you see.
Now, what's the unique information that
The-
we
if
still
you-
get from terrestrial observatories that we cannot get from
You see,
space?
the thing is that in order to get spectra, for example, you need very long observations. And then the bigger the telescope, the fainter is the object that you can see. So at the moment, the biggest mirror that we have in space is a JWST mirror, which is 6 meters. Then if the 30-meter telescope, there are 3 like that being built, okay, so it will have about 30 meters diameter. So 30 by 6 is 5. Okay, the square of 5 is 25. So 25 times the collecting area. So, and then the disadvantage from the ground was the atmospheric blurring. But with adaptive optics, so this will compete with the space telescopes. And also they are far, far cheaper. So one day, one of the American astronomers was very bitterly saying that the cost in keeping the HST going round per year is the same as the cost of building a Keck telescope. So cost and technology.
And the second thing is, this is a curiosity. We know that there are lots of atmospheric, lower stratospheric gases that are light absorbing, right? Infrared, ultraviolet. Now with those kinds of man-made gases expanding in the lower stratosphere, what will be our ability to see these distant objects?
Yeah, you see that everything is going to be impacted. But more important than is the light pollution. Okay, and the light pollution which comes from the cities.
Yeah,
but
that's illumination.
Yes, but the worst is that you know that they're going to send out these clusters of thousands of satellites, small satellites. Each one of them emits light, and there will be many in the sky at any given moment, and that is going to be incredibly bad, both in the optical as well as in the radio. So there is the International Astronomical Union has established a group of people, a center to deal with this. And you talk with the satellite people, and you say you can paint it in a different way, you can have the reflectors in a different way to reduce all this. So atmospheric gases are bad, but the light pollution is worse.
Hello, sir.
Yeah.
First of all, really thanks for such a wonderful and interesting information. So, according to me, in the universe, very small as well as very large thing is having its own role. So, in your talk, you mentioned about dust cloud. Can you please elaborate about the role of dust cloud in the universe?
Yeah, you see, what happens is that when the universe was first born, it was very pristine. Okay, so it was mainly hydrogen and helium. And then there's very small amounts of heavier elements were created in the Big Bang. But when the first generation, when the star, how does the star is created? Because there's a perturbation. And then the amount of gas becomes so large that its own gravity pulls it in. So at that time, it keeps going in, and it reaches a point where the pressure due to the heat which is generated is enough to counterbalance gravity, and then you get a star. Now, those details depend very much upon the quantity of dust. And what is dust? Dust is just fine grain, heavy elements. And where do they come from? They come from the first generation of stars. Okay, so first generation of stars they are in a dustless thing. But when they evolve and when they expand and when they have supernovae, etc., or planetary nebulae, they put these heavy elements into the air, and those form dust. Okay, so therefore dust plays a very important role in the evolution of the galaxy.
Okay, thank you, sir. If time permits, can I ask one more question? Okay, thank you.
Thank you, sir, for a very informative lecture. And I want to ask some curious question. We discovered around 118 elements on this earth. And what about on the properties of these elements on the exoplanets or other planets? Maybe especially size.
Yeah, you see, helium was first discovered in the sun. It was not discovered on the earth. Okay, so like that, there could be elements there, but you see that as you make them heavier and heavier, they become unstable. Right? So, but there could be new compounds, new things that you will discover. For that, what we have to do is that we have to establish the known spectrum very well. Okay, that requires a lot of calibration, lot of understanding. And why are these lines? What are these lines? What is the nature of the lines? What are the shape of the lines? And once you do that, then you will start discovering anomalies. And those anomalies will lead you to new discoveries.
So it can possible to variation in size of elements?
That I don't know, because you see that I only understand that the heavy elements are generally not very stable. Okay, so if they are there only momentarily, you may not be able to discover it. But on the other hand, even known elements, for example, where did gold and platinum come from? They actually can't be built very well in supernovae. They cannot be built in the Big Bang, they cannot be built in the supernovae. So where do they came from? So the theory was that if you take two neutron stars and they merge with each other, okay, then you will get gold and platinum. Now this seems very far-fetched, but the LIGO detector has detected a merging neutron star, and then they did see platinum there. Right? So astrophysical processes are very important for the generation of the elements.
Okay, thank you, sir.
So my question is on the first part of your talk. Yeah, I'm here. Yeah. So about the lens or mirror technology, optics.
Yes.
So there was one news around the COVID time that some European startup or some companies trying to make water-based optics somewhere in Himalaya actually.
Oh, it's not water-based optics. What you do there is mercury-based.
Mercury-based, sorry.
Yeah,
so was it successful? Or
Yeah, it's working.
It's working.
Yeah, I mean there are problems, but those are technical problems. What you do there is simple. You see that you take a disc of mercury, okay, and then you rotate it very fast.
Yes.
Okay, then you know that you make a parabolic shape. You can prove that. Okay, so then it becomes a mirror, right? And then it can act as a telescope. The only problem is that you can't tilt it. If you tilt it, the mercury will pour out. Right? So it's a fixed telescope, and you go on rotating it, and then you have to see only the part of the sky which goes across. So it is there. Not in Nainital. It's observatory close to Nainital.
Okay. Thank you, sir. The second very brief question is about the energy requirement of the future extraterrestrial explorations. So where the energy will come from?
Sun. Okay, because JWST needs 2 kilowatts, and so it has got this thing which is, they say the area is like the area of a football field, the mirrors, and then so you'll have to depend on the solar energy.
So there is another question. Since you were talking about multi-messenger astronomy, so what are your thoughts about neutrino observatories? Since last year we got a picture of a sun which was behind Earth.
Yes.
So what are your thoughts about combining neutrino, light?
Yeah. Neutrino, yes. I forgot to mention neutrino observatories, and there's a great problem in detecting neutrinos. Okay, and then so if you have hydrogen being converted to helium, then you must have a certain number of neutrinos coming out. And there's a great problem in detecting them, even though they made these very big detectors. So therefore, it was believed that astrophysics is wrong. Okay, but then it turned out that you're not detecting neutrinos because they change along the flight path, you see, from one kind to another. So neutrino astronomy is a very well developed thing, and you see neutrinos from emerging neutrons all over the place.
The last question. Because we have no, you got a chance. Someone else. We have passed on the last question.
Well, thanks for the very insightful talk, sir. I have a question, based on what I've read. I know about the expanding universe theory, and I also know about this Goldilocks zone and the reason why life exists on Earth. So, possible to make a comment on how far the universe can expand and till how long we can anticipate life on Earth?
See, these are not very well connected, the two things. Okay, the life on Earth, we know pretty precisely. The age of the sun now is about 4.5 billion years, and it is what we call in the prime of life. In a couple of billion years more, it will start evolving, and then it will start expanding and so forth. And somewhere at that point, our life will be gone, because it expands, it changes temperatures, and then it could engulf the Earth. It can go up to Mars, the orbit of Mars. Okay, so that will happen in 4.5 billion years or so from now. So there's nothing to be worried about immediately. It's not meaning that you can't run an insurance company for this risk thing, right? But on the other hand, the universe has been around for about 13.5 billion years, and there's reason to believe that it will always keep expanding. Right, and then it's not only expanding, but it's accelerating. That was another Nobel Prize winning discovery. Right, so, and then the universe is also infinitely large, and that is the current belief. But it could have been finite size, but it is not, it's infinitely large. But what we can see is a finite size. Even if there are infinite number of galaxies, you'll see only a finite number of them. That is because as you go further and further, you are seeing light earlier and earlier. And we are already using the JWST and other big telescopes. We are already seeing galaxies when they are being created. And after that, there will be nothing. Okay, so we can only see a bubble in the universe, but the universe itself is infinitely large.
Thank you, sir.
Okay.
So
Yeah.
now there is a last question and no more last.
Yeah, thank you. It was a very nice lecture. I have one question. Like, can you provide some insight on the multiverse hypothesis?
Yes. See, what happens is that, so there is our universe. And let us say in various ways, it is an accidental universe because there is a fine tuning of certain things. So the question is this the only kind of universe? Or could I had other region of stability quite different from this? That's one consideration. The other consideration is that, see, topologically, I mean, you can imagine that our universe is a plane. Just for a moment, it's a plane in multi-dimensions. But so can there be another plane and another plane and another plane? So when you combine the thoughts about cosmology with thoughts about quantum mechanics, okay, then you could have these different things. Now, if I say that there are 10 different universes, again, it makes no difference to anybody, unless they can see a signal from that to here. Right? So, and then how do you go from one multiverse to the other? So it will require what are these tunnels and things like that. So essentially it is a play on the 4-dimensional geometry of the universe. So it is just like when you go to Khandala from here and across, you go through the tunnels and immediately come to a different region. There could be tunnels in 4-dimensional space-time which could allow you to do that. That is in principle possible. But whether in practice it is achievable is another matter. Okay? Thank you very much.
Thank you, Ajit, for this, like, not only this amazing talk. Yeah.
Thank you very much.
But the way you answered our questions, you know, they are probably very naive questions to ask, but, and thanks to the audience for being very interactive and asking questions. Now I would request Ashish to present a memento to Professor Kembabi. Yes. No, that's switched off.
These are all research students and scientists from NCL. So if in a multiverse, they might have become astronomers and we could have become chemists. So we are all the same. That's a very nice thought. But I'll tell you another thought which is very sobering. We always blame the bureaucrats. Okay, and the bureaucrats are all IAS officers, etc. And many of us have been told by our parents to become IAS officers when we are young. So it was predicted long time ago, 10 years ago, that I'll become an IAS officer. I could easily have been that. So when we blame the bureaucrats, we should remember that if we had been bureaucrats, we would have behaved in the same way.
Thanks for this nice insight. So, yes. So we have a little detour from the program. There is an item I'll request Dr. Rajesh Gunade to come on stage to steer the formal launching of NCL's Central Analytical Facility. Rajesh.
Thank you, Dr. Sarika. Good afternoon to all of you. And friends, on this auspicious day of NCL 73rd Foundation Day, we are very pleased to inaugurate and launch the Central Analytical Facility. The facility actually houses the state-of-the-art instruments particularly analytical instruments, and it is dedicated to provide the analytical research, technical services. In addition to that, the high level of expertise and guidance to audit users. The main objective of this facility is to have a single window system for all the sample analysis. Other than that, the objective is to enhance the utilization factor of all the equipments, and not only that, actually generate operating cost of the equipment. So that was another objective. The third objective is to make the facility available to all the users, uninterrupted and easy access to all the facilities. So that was one more objective of this particular facility. The scientists and the staff which are going to be associated with this facility are committed to deliver research collaboration, technical services, advice, guidance, training to the researchers, not only the internal researchers but the outside users. So today we are going to launch this online requisition systems for its internal users. From today onwards, please keep in mind, from today onwards, we are not going to take any hard copy of the regulations. Okay, so you are all encouraged to make each of these. Please, if you are not registered, kindly register it and submit all your equation through the online equation system. So, furthermore, we fully agree and understand that any new developed website will have some bugs, some errors and all, and need continuous upgradation and improvement. But in this period, we need your feedback and inputs so as to improve the system to a great extent. So you are requested to bring to our kind notice any changes that has to be made to the website. Okay. So to inaugurate this facility, and I request Professor Ajit and Dr. Ashish, along with my colleague Dr. Suresh Bhatt, to please come over the dais and please inaugurate the facility. So this is the website, new website, where we can browse all the instruments, and the details about instruments can be seen once you go to this website. But I assure that the facility is available to all of you, so kindly make use of it. Okay. So
I think it is okay. We don't have time so much now.
anyway, so I have already shared the website link to all of you. Kindly browse through that one. Okay. So I just would like to thank to all the people who have contributed to develop this website. The developer, of course, the Dr. Nikhilesh Yadav, Ms. Vaishali Yadav, all my PH, then the CAP staffs and everybody. Thank you all for your support. I also would like to thank all the facility, all the representatives who actually gave us all the suggestions and to improve this website and all. So all HODs, all the division representatives and all. Okay. And thank you very much.
Thanks, Rajesh. So next I'll request Mr. Santosh Kadam to steer the students' dance.
Thank you, Dr. Sarika. Yeah, good afternoon, ladies and gentlemen. Before starting this program, I would like to introduce NCL Research Foundation. NCL Research Foundation is registered as a non-profit public trust, and it is supported by the donations made by different individuals and different companies. It is managed by distinguished board of trustees from different sectors like academics, industries, and public life. As you know, every year on this occasion, NCL Research Foundation gives merit awards to the children studying in class 9 to class 12. These are the children of NCL employees in Group D and support staff in Group 1. So I request dignitaries to please come forward and hand over the awards. So the award carries a cash prize and a certificate. There are 7 awards this time, and these awards are for last 2 academic years. So there are 7 awards. I'll request the children, once I announce their name, please come forward and take the award. The first award is to Kumari Sadhika Rajendran for class 12. I think she is not a... The award carries cash prize of rupees 4,000 and a certificate. The next award is to Tania Jagdale for class 12. The award carries cash prize of rupees 4,000 and a certificate. The next award is to Shantanu Gaikwad for class 12. The award carries cash prize of rupees 4,000 and a certificate. The next award goes to Kumari Niveda Varadrajulu for class 10. The award carries cash prize of rupees 4,000 and a certificate. We have next child who has got 2 awards, one for class 10 and other for class 11. The award goes to Master Vishesh Yadav. Vishesh is not here, so her mother can take the award. The award cash prize of rupees 7,000 and 2 certificates. The last but not the least, the award goes to Pritika Rajendran for class 11. The award carries cash prize of rupees 4,000 and a certificate. Congratulations all the awardees. I request one group photo if children are available here. Pude yeta ka? Can you please come forward? Parents also can come forward, please. Parents also please come forward. Congratulations to all the awardees. Now I request Dr. Sarika to take over for vote of thanks. Thank you.
Hello. Yeah. Thanks, Mr. Kadam. And as any, astronomy knows how many people you need for any successful experiment like that. To have any successful event, there is a big group behind the scene who are working. So I need to thank them. First, the event management team, Mr. Sunil Patel, Dr. Nikhilesh Yadav, Ms. Sonali, Shri Ganesh Mane, Mr. Hari Krishna Punjal, Mr. Jagtab, Shri Avinash Devtale, Shri Sanjay Askar, Mr. Javed, Mrs. Asha Shinde and Mr. Deepak Jori. And also I would like to thank Mr. Atul Mahajan, Mr. Jaipal, Mr. Yogesh Mahajan and Mr. Mani. Thank you. And thank you all for participating.
Entry into the